Today, I will present a model-based feature selection for neural network based on mixed integer programming approach. This is a sub-project under the project AI techniques for power system under Cyberattacks. The project team include myself, Jan Cronquist, which is also the PI of the project, and Calvin Sen from Imperial College London. This small project, we focus on the robustness of deep neural networks. The importance to keep a maintain robustness of the neural network is to protect the neural network from this adversary data, which only has a small perturbations added on the clean data. But with the small adversary perturbations, the image will be misclassified. This can also appear on much simpler datasets, amnesty datasets for number classifications, with small dots added on those green scale pixels, even very little to notice, but still the neural network will give wrong labels for each of the number. If we train the neural network with better robustness, then it will be more stable even with test data with the adversary perturbations. And we will focus the input feature selections method, which will reduce the number of input parameters in the model. In this way, not only we can have a much smaller size neural network, and also we can improve the robustness and the stability of the model. The previous method includes the drop-off method and regularization-based methods, but they are not very informatic about the feature selected by those approaches. So instead, in this project, we will select features by optimizing a pre-trained neural network. And we focus on two benchmark dataset, amnesty dataset, and the fashion amnesty dataset. Both have green scale image of the same size and the same number of classes. And we will focus the deep neural networks with two hidden layers of same size, where two consecutive layers are fully connected and with a ReLU activation function. And to utilize the pre-trained neural network in the optimization model, we need to encode the map on each neurons in the neural network, where the input data X is passed by the neuron to the output variable yi, and yi equal to the non-negative of the linear combination wi transpose x plus bi. And wi the weight and bi the bias. To encode this map, especially the nonlinear operation, which only take the non-negative part of the pre-activation value, we will use the big gamma in formulation and use the integer variable sigma to indicate if the pre-activation value is negative or non-negative. When it's negative, we have these constraints work together to make sure yi equal to 0, otherwise yi equal to wi transpose x plus bi. In this way, we can encode all the map in the neural network and formulate the whole neural network in the optimization problems. And the spaces, we have the optimal sparse input feature selection problems, which aim to select at most L0 number of features from the input image, such that the classification confidence for a certain class I is maximized. This picture shows the result when we change different cardinality number L0 from 10 to 20 and 200. You can see in the last pictures, and since the case we have class equal to 0, you can see the shape of the number 0 appear more obvious when the cardinality number increase. Based on the OSRF problems, we can iterate all different classes and union the feature selected by solving each of the problem. And on this basis, to further control the total number, we modify the constraints such that the cardinality constraints only works first on input features that are not selected by previous iterations. Therefore, in each iteration, we always select distinct features, and we can control the total number easily. Also, to further improve the performance of this approach, we add the distribution constraints to force the selected features spread over the whole input image. And here the picture shows the case when we partition along both sides of the image with two subgroups. In this way, the whole image is partitioned into 4 equal-sized small blocks. And with this partition, we then force the cardinality on each submatrix is around the similar number, and that's make sure we select features more evenly across the input image. And the picture here shows the case when we force the distribution constraint in the model. When k equal to 1, you can see there are pixels clustered in the same closely in the final selection. But when k equal to 2, then this feature selected are more spread over the whole image. And this also leads to a better accuracy in the test data. Okay, here it is the final OSRF model. This is the final algorithm where we iterate over the 10 classes with a pre-trained neural network. And in the last part, I will show you some numerical results where we compare our method with other feature selection methods to show the accuracy of the model trained with the sparse input selected by different methods. And these 3 feature selection methods we compared with include a random sampling method and also a data-based feature selection. In the case, we prefer to choose pixels that has higher, features has a higher value in the pixels over the whole trained data set. And the third method with the weight-based feature selection, we also need the pre-trained model where we select features where the sum of the absolute value of the weights from the first layer across the whole data set has a higher number. The 2 tables when we test the methods, different methods on dataset MNIST and fashion MNIST. In both datasets, our methods always have the highest performance, and the accuracy with the sparse input feature selected by our method also very close to the accuracy when we train the same type of neural networks on the full input feature dataset. And here we colored the results by the data-based methods in red in the second table, because even though it works also very nice with the MNIST dataset, but with a bit more complicated dataset, which is the fashion MNIST dataset, the performance drops very obviously or dramatically. Okay, the last test, we aimed at the robustness on the adversary input. And to test the robustness, we measured with the adversary radius epsilon. So when epsilon gets larger, then means the model gets more robust. This here in this tables, we showed the improvement percentage compared to the robustness on the model trained with 4 inputs features. You can see when we only use 50 inputs, and we can achieve at most 19% on the robustness. To conclude, this project focused on input feature methods, which aim to reduce inputs, the input size of the model, and still maintain a very good classification accuracy. And also on this basis, we tested the neural network, and the result shows the robustness can improve a lot as well. And next step, we can generalize this idea to more complicated architectures, such as the CNN model. And we can also work on improve the optimization technique to reduce the computation expense on solving each MLP problem in the algorithm. And that's all. Thank you.